that have a damaging effect. So these are the two major things. Even if you have done what you are supposed to do, you know, maybe you've collected your data set, your sampling frame is good, your sampling design is fine, and everything looks good. If you don't investigate the model assumptions, or you don't investigate the presence of unusual observation, I want to tell you that you may not have a good model. Okay, so before I move forward, is there anyone want to ask question? Is there anyone? Can you guys hear me?
Yeah.
Okay, thank you. So I'm going to go to the next slide right now. Okay, like I said, uh, you know, I want to show you on this slide, I want to show you the difference between a scatter plot and a residual plot. Okay, now what you are seeing on my left hand side is a scatter plot. Okay, what do I mean by a scatter plot? What I mean by a scatter plot is that I want to have a direct plotting of the two variables. Okay, having a direct plotting of the two variables, that's what we mean by a scatter plot. Okay, and for it to be linear, you know, it should be this way. Okay, now if I want to do residual analysis, okay, you know, in the analysis of residual, what do we always want to do in the analysis of residual? What we actually want to do in the analysis of residual is to be able to investigate whether assumptions are violated. I'm going to say that again. What we want to do in the analysis of residual is to be able to investigate whether the assumptions of a linear regression model is violated. And why are we analyzing residual? We are actually analyzing residual because assumptions in the linear regression model are centered on the error. If you look at all the assumptions that I walk you through in the linear regression model, actually centered on error. And you know what? We got a way to estimate error. An estimated error is called residual. I'm going to say that again. An estimated error is called residual. Okay, so what I'm trying to do right here is like plotting residual against the independent variable. Okay, plotting residual against the independent variable. Okay, the assumption, one of the assumption is that when I plot residual against the independent variable, there shouldn't be a pattern. Look at that. Do I have any pattern? If you look at this one now, it doesn't have any trend. It doesn't have a pattern. Okay. So if it doesn't have a pattern, and that means uh, uh, the error time have actually behaved in a way. Okay. And that actually justifies the linear relationship that I talk about right here. Okay. So in the residual analysis, where I plotted residual against the predictor, so you actually expect, we don't expect to have a pattern, you know, you know, it should be random. You can say this is like a random stuff. Okay. So this is actually agreeing with this. Okay. Now, when I take you to, um, okay, before I do that, I think I'm going to do something right now. Now, if you look at this center here, okay, and you look at this particular point, okay, you can actually measure the distance, okay, from this side to this side, and look at that. Look at the, if you look at this one, okay, and you look at this one, they are at equal distance to this line. Okay, they are at equidistance to this. It means the residual analysis will enable us to scale okay, the vertical axis. Okay, so the vertical axis, what do I mean by the vertical axis? That is, I've been able to scale this. I've rescaled the variable here. So rescaling that, of course, this is what I have. Okay, and that will going to ensure an equidistance. You understand what I mean? Okay, so and that's exactly what we're trying to. Uh, More about that. Uh, if you look at the data set that I showed you before, you know, I've already walked through the scatter plots. I can also show you the residual plot, the corresponding residual plots. And there's something I'm actually going to show you right now. Look at the data set 1. Look at the scatter plot. Look at the residual plot. Now, look at the data set 2. The data set 2 has a curve, right? It has a curve. The residual must have a curve too. In fact, it's going to be a perfect curve. So this is more or less looking like a quadratic curve. Okay. Now take a look at the data set 3, where you have this. You know, we are suspecting kind of an outlying observation. And take a look at that. This is a corresponding residual plot for that. And this guy here is a corresponding data set for me, the scatter plot for data set 4. So the difference between them, you're going to notice that we are talking about line. You can see a line here, but there's nothing like a line here and here. Can you see that now? Okay. And in the case of a straight line relationship for data set 1, you don't expect here, you don't expect, because I know some of you will be expecting that, okay, when I have this curve here for this data set, I also have a curve here. Okay, why is it that for the straight line one, why is it that I don't have a straight line here? No, the assumption for straight line is that the residual plot must be random. You know, you should have a random point. Okay, you know why? Because of the fact that our random component, we call it a random component. The error is a random component. Okay, so therefore it should have a shape like this. Okay, it shouldn't have a pattern. Okay, so please, what I just showed you right now is just to be able to show you the scatter plots of different data sets with their corresponding residual plots. Okay, I want to take you back to assumptions of simple linear regression. Why am I taking you back? I'm actually revisiting this because, you know, we said we want to investigate whether assumptions are violated or not. And it is necessary to actually revisit this assumption. So, you know, I've walked you through this assumption before, and you know the implication of these assumptions. There's one that talk about linearity. There's one that talk about independence. There's one that talk about normality. And there's one that talk about equal variance that I also call homoscedasticity. So, and if you can see in every one of them, okay, the assumption is basically on the error term. Okay, so, and you know what? We got a way to estimate the error time. And when we estimate the error time, we actually have residual. Okay, and that is the reason why we're going to be having analysis of residual. Now, what I want to walk you through now is how does a residual plot look like? Okay, so I'm actually going to show you how residual plots look like. You know, a very good residual plot should look like a random noise. Okay, when I say random noise, it should be something that doesn't have a pattern. Look at that, it doesn't have any pattern. Okay, so when we see something like that, we actually going to say, okay, our error is purely random. Okay, so and then we can actually use the residual plot to be able to tell the world, okay, that there is no evidence of linear relationship, or there is an evidence of linear relationship. Okay, so if you look at this, if you plot your residual against the variable, and you got something like this, then this is an indication that the linearity assumption has not been uh, has not been violated. Okay, so that was why I said there is no evidence against this assumption, so it means the assumption hold. Okay, now the next thing now is looking at the assumptions of equality of variance. Okay, so when you take a look at this, okay, when you take a look at what I have right here, you're going to see that the data points, you know, they have equal variances. And when I talk about equal variances, it's just like the rate at which, when I look the variance of the residual given any value of this, okay, the variance of residual given any value, whether given -2, given -1, given 0, you're going to see that the variation that we notice right here is more or less as the variation that we notice right here is more or less as the one we notice here is more or less. Though pictorially, the way we are diagrammatically, we may not be able to say per se whether the assumptions of equal variance is violated. We have a standard test that we are still going to carry out. Okay, we got a standard test that we're still going to carry out to be able to conclude whether the assumption is violated or not, because there can be a kind of conflict of interest in the interpretation, or on whether the variance of residual at any given value of this, whether they are constant or not. And you know what, from what I'm seeing right now, we cannot actually tell, from these plots whether the residual is normal. Okay, and if we cannot tell, then what kind of plots can we use? Then there's something I call a probability plot. Okay, that I'm going to show you. We call it a normal QQ plot. Okay, the normal QQ plot can actually be used, to test if if the error time is normally distributed or not. Okay, so this particular plot, the residual plot, cannot be used to answer a question on whether normality assumption is violated or not. So we're actually going to use a normal probability QQ plot that I'm still going to be telling that I'm going to walk you through in the subsequent lecture. Okay, and I don't think we can also tell from this plot on the independence. Okay, so which means if I want to use residual plots, so this particular plot right here, we can only talk about linearity and equal variance. Okay, now which assumption is violated? It's good to be able to ask, okay, to be able to know which assumption is violated. But you know what? I can give you something like this, okay, and be able to ask you which assumption is violated, okay? And of course, you can actually see these violate the assumptions of equal variance. Look at that. If I'm looking at the variance of residual at 0, 1, if you look at the variation exhibited here, is different from the variation exhibited around here, is different from the variation here, is different. So the variation here is even great compared to the variation here. Because of that, because for the variation to be equal, for us to have equal variances, the variance of the residual at any given value of x, must be equal, they must be the same. So as you can see right here, what is violated is the equality of variance. Okay, the equality of variance is violated. And let me tell you something. One assumption may be violated, and you know what? Another assumption may not be violated. And you know what? There is possibility that even all assumptions are violated at the same time. Okay, so from what I'm showing you right now, assumption that is violated is the equality of variance. Okay, now if you look at this one now, I can also ask you what assumption is violated. As you can see, the shape right here is different from the shape right here. Okay, and the assumption that is violated, of course, you know, it is a curve, right? Let's look at a curve. In fact, from what I'm seeing right now, it's looking like a sinusoidal. Okay, in wave, you know, a wave motion. It's looking like a sine, like a sinusoidal. Okay, so this actually violates the linearity assumption. And why this violates uh, assumptions of equality of variances? Is there anyone who need more clarification about how the equality of variance assumption is violated and how the linearity assumption is violated? Is there anyone who have any trouble time?
Yes.
Okay, go ahead.
Yeah, I'm slightly confused about the linearity one. I mean, I can definitely understand the plot that you showed us violates the linearity, but if if the if the plot is like a kind of like a straight line,
Okay.
it's like probably a straight line go up. Is that also violates the linearity, or
Uh,
that would be
okay. Let me tell you, that's a very good question. If you take a look at this guy here, okay,
yes,
we are actually working on this, a residual plot,
yes.
okay, and you know what? Uh, the reason why this violates, I'm going to take you back to what I projected before.
Oh yeah, I
Okay.
think my true question is like why data set 3 does not fit linear regression.
Oh, you mean data set 3?
Yes,
Oh, it's not as if linearity is not violated in data set 3, but
yes.
there is, we are suspecting a point here that is an unusual point.
If we don't have that point, does
Oh,
data
of
set
course. Of
okay,
course. If you don't have this point, everything is fine.
okay.
Have I answered your question now?
Yes, yes.
Okay. And that was the reason why there are two things that need to be investigated. And you know what? They are not mutually exclusive. Number one is model assumption violation. You know, you need to test that.
Mhm,
And unusual observation. Okay. So in data set 3, this particular point look unusual. It
mhm.
look unusual because it's not consistent with the rest. Okay. So is there any question before I go forward? Okay, so I think you guys have seen, you know that in exam, uh, I can actually give you, you know, a plot like this, and I can actually ask you which assumption is violated. Now you know how to tell, okay? You know how to tell that a linearity assumption is actually violated right here. Why the assumptions of homoscedasticity that we call equal variances is actually violated right here. Okay, and you know what? This is using the plot. I also want to tell you we got a way using the formula to test. You know, so because of the fact that we got some set of individuals that may not be able to read the graph correctly, and that was the reason why in the subsequent lecture, I'm actually going to walk you through standard statistical procedure to test uh, this violation. Okay, what I want to talk about now is what I call unusual observation. Okay, unusual observation is what we call outlier. Okay, outlier in a data set. Okay, is is when you have, when the data when it according to Benka, he said, when you have, when a data point is not consistent with the rest. Okay, when a data point is not consistent with the rest. Okay, so, and in most of the situation we can call it an extreme value. Okay, and that was why I said the extreme y value, the observation does not fit the pattern of the rest of the observations. Okay, and you know what, in addition to, or before I move to leverage, because when I'm talking about unusual observation, it could be outlier or it could be a leverage. But let me talk more about this outlier. Uh, Let me tell you something. Uh, Outlier can be, there are so many sources of outlier. Okay, it could be through erroneous imputation. Maybe by the time you are recording and you have kind of mistake, you recorded a value by mistake. Maybe instead of you to write 500, maybe you forgot, you now write 5,000 and you now analyze it like that. That is one of the sources of uh, outlier. So what we do is that if that is the source, then that particular data point can actually be excluded, can actually be discarded from the rest of the data point. But you know what? It is not all the time that we discard outlier. It is not all the time, because we actually need to investigate, the source of the outlier. It is only when the outlier, it is only when the source of the outlier is attributed to erroneous imputation that we can actually discard it. But in a situation where the outlier is a genuine observation, okay, then you actually need to have a way to model that. That's what we call robust statistics. And I'm also going to talk, I'm going to walk you through that in the subsequent lecture, okay? Because in that robust statistics, just to tell you that, okay, this is an outlier that I've identified, and this outlier has a tendency to cause a damage, has a it poses a threat on the decision I'm going to take. Then what I need to do, I actually need to resort to robust model, robust way of handling that. Okay, what do we mean by robustness? Okay, robustness is ability of a model, okay, to perform very well even in the presence of an outlier. Okay, even in the presence of unusual observation. Okay, if the model is performing very good, so which means this model actually uh, you know render the effect of the outlier useless, or the effect of unusual observation useless. Okay, so we have robust statistical modeling. Okay, so what we're doing right now is not a robust statistical modeling. Okay, so this is just like, okay, this is what happened. Okay, so what can we do? Okay, should we discard it, or should we model that like that? Okay, and if you want to model that like that, of course you have to go beyond what we're doing right now. Okay, so another thing, another unusual observation, maybe, we could have an extreme value that have high leverage. Let me tell you something. Extreme value may not necessarily be an outlier. An extreme value may not necessarily be a high leverage point. Okay, but you know what? An extreme value could be outlier. An extreme value could be high leverage points. We can have a situation where in a model A model may have a problem of an outlier, and a model does not have a problem of high leverage. We can have a situation where a problem may have a model may have a problem of high leverage and may not have a problem of outlier. Okay, that is still a problem. And we can have a model that have the two problems. That's a double tragedy. Okay, so now what I want to walk you through right now is to be able to tell you that if outlier is present, we actually need to have a way to deal with it. If high leverage point is present, we actually need to have a way to deal with it. Okay, now what I want to walk you through right now is we're going to have a formula uh, that we can use to figure that out. Because number one, we need to investigate whether there is an outlier, and when we compute a particular value, like from a particular estimator, okay, there's a value we must not get. Okay, so if we get something beyond that value, then we're going to say, oh, this is an outlier, and this may have a potential effect on the model. Okay, so I'm going to be walking you through that. But you know what? I'm going to start from this. Having a high leverage point that is not an outlier. Okay, you can have it, like I said, a leverage point may not be an outlier. Okay, take a look at, I'm going to show you something right now that you're going to, now take a look at this guy here. Okay, oh, this makes sense. Okay, but take a look at this one here. Look at this. There's a particular point. Oh, can you guys see what I'm pointing at right now?
Yes.
Yes.
Thank you so much. Thank you so much. Now, can you see that this point right here is on the same straight line with other points? Okay, so this particular point is not an outlier, but it could be a high leverage. Okay, in a situation whereby you got a point that is far away from other points, but it's on the straight line with other points. That is not an outlier. Okay, because an outlier is expected to, is going to go off the line. Okay, so this is an example of high leverage. So okay, this is an example of high leverage. So this guy here is not an outlier, but we can actually investigate that for high leverage. Okay, now right now I want to talk about an outlier that is not a high leverage. Okay, this is the standard. Oh, this makes sense. But take a look at this guy here. Oh, look at this point right here. This particular point is not on the straight line with others. Therefore, but despite the fact that it is not on the straight line with others, this is not a leverage point, but this is an outlier. Okay, this, what I have here, is an outlier. So it's an outlier because it is not on the same straight line. Okay, it's different from the leverage that I actually have here right time. This is a distance apart from the rest of the points, but it's still on the straight line. The fact that it's still on the straight line, that does not make it an outlier. But you read, but right here, this is an outlier. Okay. Now, the next scenario is, adding an outlier who is also a high leverage point. This is what I call a double tragedy. Okay, it's a double tragedy, and let's take a look at that. Oh, take a look at this guy right here. This guy is not on this particular, can you see that straight line? It's not part of this straight line. And not only that it's not part of the straight line. Okay, so the fact that it's not part of this straight line, that makes it an outlier. And at the same time, this guy here has a high leverage point. Why does he have a high leverage point? You can actually see that this particular point right here, if you look at most of the points, okay, the most of the one that you have right here, they are, actually between this point and this point. You get that now? But take a look at this guy right here. So we can actually investigate, okay, for this, okay. So, but when we use a diagram like this is just to suspect, okay. And when we suspect, we can actually carry out the test. We still have a statistical procedure to carry out the test, okay. It's just like you are driving and police pull you over, okay. It is not everyone that police pull over that will get a ticket, okay. It is not everyone that police pull over that will get a ticket, okay. So but before a police stop you, okay, before the police pull you over, he must have seen something, okay. Maybe he's suspecting you, okay. So if we want to, so in statistical analysis, okay, when we do data exploration like this, okay, when we plot graph and plot like this, and that will enable us to have a suspect something, okay. And when you suspect something, then we're actually going to carry out a statistical test to be able to see whether what we suspect is actually true, okay. It is not all the time that is going to be true. So we got a standard way, okay, to conduct a test, okay, on this. Okay, we got two measures for detecting outliers, okay, and I'm going to discuss the two measures. The first measure is residual, and the second measure is by standardized residual, okay. I'm going to walk you through these two methods, okay, of investigating. I don't know whether you guys have come across something. When you run a simple linear regression in R, okay, the question is, how will you have access to this? Okay, do you know that if you write plots into whatever, yeah, if you write plots, okay, on this, like if you write plots bracket or this one, it's actually going to give you a different kind of plots, okay. And then among the plots you are actually going to have is going to be this one here. So this is a plot of residual versus fitted, okay. And you know what, when I plot residual against fitted, I expect a random pattern, okay. I expect a random pattern, okay. So I can base detecting outlier on just analysis of residual, okay. Look at all these points right here and look at this guy here, number 21. You may be suspecting that this guy is far away from everyone, okay. So this could be an outlier, okay. So, but you know what, we got a way to carry out this test statistically, okay. So you give me 1 second. I need to put off this one now. Okay, thank you for that. So we got a way to investigate that, okay. So we got a way to investigate that statistically. Now, if you look at what I have here, okay, this is residual plot, but this is not a residual plot. This one has been standardized, okay. This has been standardized, and you know what? Here, if I want to know what is plotted here, what is plotted here is a standardized residual, and if I want to standardize that, I'm going to use the formula right here, okay. The error divided by the standard deviation. Of course, you know this, right? That we obtain from the regression output that we called residual standard deviation is this guy, okay. And I'm going to tell you how you can figure out HII. Okay, the HI, you need to get this one before you can actually compute this. So the RI here is a standardized residual. Okay, so this is standardized residual. Okay, so I'm going to walk you through that one by one. Now, I want to use this opportunity to show you somebody. It's not just somebody. This is an emeritus professor. Cook is Robert. Has anybody heard about Cook? Professor Cook is one of my colleagues. Okay, in the School of Statistics, University of Minnesota. So this man is well known everywhere in the world. Okay, he was the one that actually gave the world a way to measure outlier. To be, if you want to dictate an outlier, if you want to know whether outlier is present in your model, okay, in your data set, okay, Professor Cook actually developed an estimator that can be used to figure that out. So, is he a member of the School of Statistics? He's a faculty member of the School of Statistics, University of Minnesota. Okay, so has any one of you met this professor before? Can you guys hear me? Okay, let me read my chat. Oh, somebody said no. Okay, he's a member of, it's a faculty member. His name is Dennis Cook. Okay, he's a distinguished professor of statistics. Is well known everywhere in the world. Okay, so this guy gave us a measure. We call that Cook distance. Okay, you can say the Cook is just from his name. Okay, Cook distance. Okay, and the Cook distance symbolically is di equal RI squared divided by 2, HII divided by 1 minus HII. And you know what? The RI here is this is I'm going to show you the expression for that. Give me 1 second. Look at that. This is expression for RI, the standardized residual. Okay, so that was what the Professor Cook actually base his formula on. Okay, now you can see that right now. So and there's going to be a threshold when I compute di from the data set in an attempt to detect influential data point. Now let me tell you something. A data point, when you suspect, maybe using a plot, when you suspect a data point to be an outlying observation, you actually need to compute a Cook distance. You need to compute, you need to make use of this formula. Okay, and let me tell you something. The large Cook distance means